welcome to the Dark Carnival Super Show. You're a specially invited guest, and I'll tell you what for. Cause you're the evilest pedophiles, rapists, and abusers. All together we've got 50,000 of you losers. You're all about to witness an incredible...
Welcome back to pentagramprime. Today's lesson will demonstrate a useful trick for performing many types of derivatives, including, of course, inverse trigonometric functions. We'll begin with the derivative of arcsine of x, and I really don't know what possessed me to try turning these things into bats. Blame Chris Nolan. The first step will be to assign a variable for arcsine of x, shown here as y. From here, take the sine of both sides. This simplifies the left side, and we then take the derivative with respect to x of both sides. And the chain rule gives us an expression for dy dx. And now, we must try to figure out that thing in the denominator. I don't know about you, but I hate settling for partial credit. Intuitively, things can get a little weird when you start mixing inverse trigonometric functions with other than that of the function that it is the inverse of. You need to be able to picture what the functions are doing. So let's draw something. For a given right triangle with one of its non-right angles equal to theta, we will let theta equal the inverse sine function, and if we take a closer look at the argument of arcsine, we see that we can assign the value of x for the side opposite theta and 1 for the hypotenuse. This is per definition of the sine function. The length of the remaining side can be worked out using Pythagorean theorem. It's important to notice that cosine of theta is no different than that of cosine of y in this context. Really should have worked out a simpler scheme for these variables, but I'm sure someone will give me an earful about it in the comments. And both are equal to the adjacent side divided by the hypotenuse. So if we take the values for top and bottom, we find that cosine theta is equal to root 1 minus x squared. With a meaningful expression for cosine of y at hand, we can substitute it into the corresponding expression for dy dx. And now we have an expression for the derivative of arcsine of x in terms of x. Looking at the graph of arcsine of x, we see that the formula has infinite derivatives at x equal to plus or minus 1, and is not defined outside of the open interval from -1 to 1. This matches with the behavior of the formula above. So what about arc cosecant? Similar principles apply as with the arcsine function. You just need to pay attention to how inverse trig functions interact with normal trig functions. We start again by taking the normal version of the inverse function, in this case cosecant, and applying it to both sides of the equation. And we get an equation similar to that with which we got earlier while evaluating the inverse sine function. Taking the derivative of both sides with respect to x gives us an expression for dy dx via the chain rule. The first term in the denominator simplifies quite easily to x, and the term to the right will require us to do as we did before with cosine of arcsine of x. Letting theta equal arc cosecant of x, we break down the argument of arc cosecant into a numerator and a denominator before assigning x as the hypotenuse and 1 as the length of the side opposite theta, in accordance with the definition of the cosecant function. Pythagorean theorem provides us with the remaining side, and we may now consider the value of the cotangent function in the context of this triangle. The cotangent of theta corresponds to the value of the length of the adjacent leg of the right triangle divided by the length of the opposite leg of the right triangle. Root x squared minus 1 divided by 1 works out to be just root x squared minus 1. And I apologize again for the fact that y and theta are the same variable. With the definition of cotangent of y in terms of x now at our disposal, we can form an expression for the derivative of y with respect to x in terms of x, and the result is negative 1 divided by x times root x squared minus 1. This finally gives us an expression for the derivative of arc cosecant of x in terms of x. And I don't know why Google chooses to switch up formulas on me like this, because I did type arc cosecant of x. Anyway, arc sine of 1 over x is equivalent to arc cosecant of x. You can see correspondence between the graph and the behavior of the function by noting the lack of a positive value for x squared minus 1 inside of the square root, as well as the way the slopes become vertical at x equal to plus and minus 1, corresponding to poles in the derivative for these values of x. Join us next week when we will delve into the nebulous underworld of contour integration and its uses for solving definite integrals. It's important to remember that people fear the most what they don't understand. It was as true for Galileo as it is for the Detroit music scene. Till next time, this is Pentagram Prime signing off. Shaggy, take it away.